Jackson back again. So in the last few videos, we've been looking at exploring the side angle side or SAS um, scenario in different geometries: Euclidean, hyperbolic, spherical, and taxicab. And one of the things that we found was that it works uh, for Euclidean, hyperbolic, and spherical geometries. In other words, those geometries, it was enough to uh, guarantee congruence of triangles, but not in taxicab geometry. So let's go over some of our conclusions here that we should have seen from looking at these investigations in the last couple of videos. So notice that in the SAS case, there's no way to specify the given measurement, so it's impossible to make a triangle in any of the four geometries we're talking about. So after investigating the other conditions in all four geometries, we will see that this is the only one of the conditions where we're given any three measurements, and no matter what we do, it is always possible to make a triangle regardless of the specified measurements and regardless of which of the four geometries we're studying. Furthermore, in Euclidean, hyperbolic, spherical geometries, any two triangles with the given SAS measurements must be congruent. Therefore, in these three geometries, the SAS measurement condition always results in exactly one congruence class of triangles for any particular choice of measurements. And given two triangles with the SAS correspondence conditions, the two triangles must be congruent. In Euclidean, hyperbolic, spherical, and taxicab geometries, the construction is very similar. Given a particular angle, there's only one point on the initial ray at any given distance, and there's only one point on the terminal ray at any given distance. This makes exactly one triangle in all four geometries. In Euclidean, hyperbolic, and spherical geometries, these will all be congruent for any specified measurement, regardless of the orientation of the original angle. However, in taxicab geometry, we saw that the story is different. In Euclidean geometry, rotations map a preimage, such as a triangle, to a congruent image, preserving both angle measure and distance. However, in taxicab geometry, Euclidean rotations preserve angle measures, but they do not preserve distances. Thus, when we apply Euclidean rotation to a triangle, the angle measures remain the same, but the taxicab lengths of the sides change. As Euclidean figures, rotated triangles are congruent, but as taxicab figures, rotated triangles have congruent angles, but not necessarily congruent sides. So the orientation makes a big difference here. In taxicab geometry, when we do the SAS construction above, there is indeed one triangle that results. However, the measures of the remaining side and angles depends on the placement of the originally constructed given angle. Specifically, the angles the rays of the first constructed given angle make with the horizontal, at least in part, determine the remaining measures. Therefore, it's easy to make non-congruent triangles which satisfy the SAS congruence condition in taxicab geometry, as we saw in the examples above. In fact, there are always infinitely many congruence classes of triangles for any particular combination of SAS measurements in taxicab geometry. And note that taxicab geometry looks so much like Euclidean geometry in many respects: planes, lines, line segments, rays, angles, parallel lines, midpoints of line segments, and triangles are all exactly the same figures. Angles are even measured the same way in both Euclidean and taxicab geometries. However, because of the different distance metrics, taxicab and Euclidean geometries behave very differently when it comes to anything involving a distance measurement. While we measure taxicab angles exactly the same as we measure Euclidean angles, and taxicab line segments are Euclidean line segments, and even taxicab triangles are Euclidean triangles, the lengths of the line segments, uh, and thus the lengths of the sides of the triangles, are much different in these two geometries. So, in taxicab geometry, triangle congruence criteria are quite different than in Euclidean geometry. And even though taxicab geometry triangles are just Euclidean triangles, they behave entirely differently when it comes to triangle congruence. In fact, this is the primary reason why we study taxicab geometry. So a very important question here is, what does the existence of both taxicab geometry and Euclidean geometry tell us about the SAS condition? So see if you can think about that question for a minute and answer it yourself before reading on. Press pause now. Okay, hopefully you took a time to think about this, and let's consider as we go further. Look at this statement here. We'll call it an SAS statement. If two triangles satisfy the SAS congruence criteria, correspondence criteria, then the two triangles must be congruent. In other words, if they have two pairs of corresponding sides congruent and the pair of corresponding included angle is congruent as well, then the two triangles must be congruent. Is that statement true or false? Well, it depends. The statement is true in Euclidean and hyperbolic and spherical geometries, but it's false in taxicab geometry. But since both taxicab geometry and Euclidean geometry satisfy all the postulates and propositions we studied thus far, and they have completely different conclusions about the veracity of the SAS statement, if we want this to be true in Euclidean geometry, it must be taken as a postulate. Here's our postulate. It's going to be our 13th postulate. Postulate 13, SAS postulate. If two triangles satisfy the SAS congruence criteria, then the two triangles must be congruent. Specifically, if we have triangle ABC and triangle A prime B prime C prime with line segment AB is congruent to line segment A prime B prime, angle A is congruent to angle A prime, and line segment AC is congruent to line segment A prime C prime, then triangle ABC is congruent to triangle A prime B prime C prime. What does the existence of both taxicab geometry and Euclidean geometry tell us about the SAS condition? Well, the SAS postulate is valid in our models for Euclidean, hyperbolic, and spherical geometries. Is not valid in taxicab, but all four of those geometries satisfy all of the earlier postulates, right? So we have at least two different models that satisfy earlier postulates, but not one satisfies SAS postulate, one doesn't. Therefore, we see that the SAS postulate is independent of the earlier postulates. So again, the SAS postulate is independent of the earlier postulates. So this is really the main significance of both the existence of both Euclidean and taxicab geometries. We mainly study taxicab geometry so that we can see that the SAS postulate is independent, that it must be an actual postulate. Now, I think the main reason we choose to take the SAS statement as the SAS postulate rather than taking a similar ASA or AAS or SSA statement as a postulate is that not only does it work in hyperbolic and spherical geometries as well as Euclidean geometries, this one is the only one where the measurement condition never produces zero congruence class possibility. It's always possible to construct a triangle given any specific measurements in the SAS measurement condition, and given any two side measurements and any proper angle measure for the included angle, there's always exactly one congruence class of triangles possible with the SAS measurements in Euclidean, hyperbolic, and spherical geometries. However, there are always infinitely many congruence classes possible given an SAS measurement condition in taxicab geometry. After taking the SAS postulate as true, then we have eliminated taxicab geometry from our study of unified geometry, and further propositions in our unified approach to geometry may not be true in taxicab geometry. In our formal list of postulates, definitions, and propositions, given and extended in our last section of these notes in the appendix, okay, you will see a line across the page right before the introduction of the SAS postulate. Material above this line applies to taxicab geometry as well as to Euclidean, hyperbolic, and spherical geometries. But until further notice, material below this line does not necessarily hold in taxicab geometry, but the results below the line will apply in Euclidean, hyperbolic, and spherical geometries. At some point, we will introduce yet another postulate, the Euclidean parallel postulate, that will ultimately eliminate hyperbolic and spherical geometries as well. Students in my class should be sure to be reading through the material in the appendix related to each section of the notes. As you work through them, you're responsible for this information, even if some of it doesn't appear earlier here. I have some other GeoGebra activities here. I think I've actually used these in an earlier video, so I won't say too much about them out here. This one is these are by Tim Brzezinski, who's excellent at developing very good GeoGebra activities. And this one here talks about an SAS proof, and what it is. You know, I'm gonna put proof in quotes. In our treatment, the way we're looking at it, we have the SAS postulate, so no proof is possible. There's no way to prove it from the earlier ones, as we see, because of the existence of taxicab geometry. But there is an alternate approach where we can take that postulate, instead of taking the SAS postulate, we could take instead a Euclidean reflection postulate that all Euclidean reflections are congruence mappings. And from that, we can prove the SAS theorem as a proposition. Prove the postulate instead of no longer a postulate, but a theorem. We're going to explore that approach more near the end of the course when we study Euclidean transformations. And it's in that context that this second activity suggests the main steps of a proof, which would have to be formally written out for the proof to be complete. So it's an idea of a proof from that other perspective. I strongly encourage you to go to these different GeoGebra activities and experiment with yourself. All the ones that I put here are publicly available, and they're all included in my Geometry Collected Resources GeoGebra book that's available online. And you can click on the activities that I make, as well as also some of these that other folks have done, like these here. I do have older sets of videos in this same playlist, including some that have a trigonometry or old version designation there. And if you see those are versions of these lectures that I put together earlier. And in some cases, most of the cases actually, they duplicate some of the material that we're doing here. These older ones were put together using Geometer's Sketchpad, which is mostly kind of out of use now, not really available. But nevertheless, they see this again and reinforce it again. I don't want to completely delete these videos. You can consider those optional in my class. Some of them were, notice that this material could be done in a trigonometry course in high school. Because you're studying about triangles in trigonometry. That's what trigonometry means, measuring triangles. And some of this same material could be used there. So we have now talked about the SAS postulate. We found out that it has to be a postulate. It's independent of the earlier postulates. We found that it works in hyperbolic and spherical geometry as well as Euclidean geometry, but does not work in taxicab geometry. So the SAS postulate then becomes our tool for working at proving other congruence criteria.